In the last video, we considered hemiacetal formation under acidic conditions. However, under acidic conditions, as I alluded to at the end of that video, the hemiacetal will actually react further to give an acetal. So how does this happen? Well, under acidic conditions, the OH group of the hemiacetal can be protonated to form a good leaving group. So assuming an excess of alcohol is present, which is how these reactions are always run, as we'll see in a couple of slides, the hemiacetal will then react with a second molar equivalent of alcohol to give an acetal, and most of this reaction goes through the familiar SN1 mechanism. And remember that a hemiacetal is a carbon bound to an ether oxygen and an OH, whereas the acetal is a carbon that is bound to two ethers. Okay, so the overall reaction for acetal formation then is the carbonyl compound reacting with two equivalents of alcohol under acidic conditions. As we will also see, this particular reaction to form the acetal has to take place under acidic conditions, gives you a molecule of acetal and water as the byproduct. Note that I will use the term acetal very loosely, whether the starting carbonyl compound is an aldehyde or a ketone. I will use acetal, but if you were being technically correct, the product formed from a ketone would be called a ketal. Sometimes you may see that crop up, and I just want to make you aware of that fact. However, many organic chemists, myself included, just use acetal for both aldehydes and ketones. So let's look at the mechanism of this reaction. And on this slide, I'm only going to go through the mechanism of the conversion of the hemiacetal to the acetal. Steps 1 through 3 of the overall mechanism we covered in the last video, where we talked about formation of the hemiacetal. So step 4 is protonation of the alcohol to make it a good leaving group. Step 5 is the leaving group leaving to give an oxocarbocation. And in this particular diagram, only the major resonance structure of the oxocarbocation is shown. You should be able to draw the other resonance structure of that oxocarbocation. Then step 6 is nucleophilic attack of the alcohol on the oxocarbocation. If we were working from the other resonance structure with the positive charge on carbon, the oxygen would be bonding directly to the atom with the positive charge, but you should recognize the depicted structure of the oxocarbocation as being very similar to the protonated carbonyl from step 1 of hemiacetal formation. And the alcohol can attack the protonated carbonyl. It can also attack, in this case, the methylated carbonyl. You break the CO pi bond and put those electrons onto the oxygen, all in the same step. Then finally, the last step, once again, is proton transfer to the solvent to make a neutral product and regenerate an acid catalyst. If you're going through these videos in order, you should be able to see some patterns showing up again and again. At the end of these acidic mechanisms, you get proton transfer to the solvent from an intermediate that has a positive charge on it to make a final product that is overall neutral. Okay, note that all of these steps are reversible, so we do have to use equilibrium arrows when drawing these mechanisms. Please, please, please don't confuse equilibrium arrows, which are two arrows, one on top of each other pointing in the opposite directions, with a resonance arrow, which is a single arrow having two heads. They mean different things. If you use the wrong arrow, you may get points taken off on a homework or an exam. Okay, so to summarize this process, a 7-step mechanism overall is the longest mechanism that you have been exposed to so far. And we did break it down into two parts. The 3 steps for the formation of the hemiacetal and the 4 steps for the conversion from the hemiacetal to the acetal. What I like to do with longer mechanisms is just take each step and attach a short label to it. So PT is my label for proton transfer, Ne is my label for nucleophile reacting with electrophile, and Lg is my label for leaving group leaving. Big and complex mechanisms are arrived at by simply taking these shorter steps and putting them together in the proper order. Also note that 4 of the 7 steps of this mechanism are proton transfer steps. So that's why proton transfer steps are the most common step in an organic mechanism. They may not seem important, they may not seem like the key step where the action happens. They're not. Well, they're not the key step. They are important. They are important in that they set up the key steps. You can't get the first Ne reaction to happen without preliminarily doing a proton transfer in hemiacetal formation. You can't get the Lg reaction to happen in acetal formation without first doing a proton transfer to make that good leaving group. The next thing I want to note is that under basic conditions, this PT reaction in step 4 cannot take place because that requires strong acid to protonate the alcohol. So if you can't protonate the alcohol to make it a good leaving group, that alcohol will not be able to leave and you will be stuck at the hemiacetal. So therefore, under basic conditions, the reaction stops at the hemiacetal. Under acidic conditions, the reaction continues all the way to the acetal, because that proton transfer step is possible. Okay, the next thing we have to consider in this reaction is the equilibrium. So acetal formation is an equilibrium reaction, and we can Le Chatelier this reaction to completion by using excess alcohol, the other reagent that's not the carbonyl compound, and or removing water, the byproduct in this reaction. So water, the equivalent of water that is formed during the reaction, can be removed effectively by using a drying agent such as magnesium sulfate. However, we want to avoid adding any extra water to the reaction, which will tend to drive the equilibrium backwards towards starting materials. Well, you may think this is a fairly obvious point. Just run the reaction without dumping any water in. But sometimes you dump water in without realizing that you're dumping water in. Namely, this reaction requires strong acid. And most acids are supplied as aqueous solutions. Concentrated HCl is a 37% solution in, you guessed it, water. So we need to be careful to choose a strong acid that is organic soluble rather than water soluble. And the most common choice for this reaction is an acid called tosic acid. Its structure is depicted below. It is sometimes abbreviated when writing PTSOH because its full name is paratoluene sulfonic acid. You don't want to say that 5 times fast. That's why we abbreviate it as tosic acid. You may remember having seen this structure. Tosic acid is the conjugate acid of a tosylate, which is a weak base and a good leaving group. Okay, to end this video, I just want to say very briefly, why do we care about this reaction? And the answer is because hemiacetals play a very important role in many biochemical processes. So carbohydrates, which we first met as being polyhydroxyaldehydes and ketones, so an OH on every carbon that's not the aldehyde or ketone carbon, can actually exist as cyclic hemiacetals through intramolecular attack of the oxygen depicted in red on the carbonyl carbon to give either a 5 or a 6-membered ring. In this case, it is the oxygen carbon 5 coming around to give a 6-membered ring. And in fact, cyclic hemiacetals are often stable enough to be isolated. If you collect crystals of glucose, what is actually crystallizing out is the cyclic hemiacetal form. And even in solution, glucose exists as the cyclic hemiacetal form 99% of the time. Okay, so that's the formation of acetals and hemiacetals. In the next couple of videos, we will take these reactions and look at them in reverse. We will look at the hydrolysis of hemiacetals and acetals under initially acidic basic conditions and then acidic conditions to give alcohols and carbonyl compounds.